Unit Overview. In this unit, we examine sorting and searching methods, which are commonly needed in a wide variety of computer applications. The unit begins with an introduction to sorting procedures. It also provides the background and formalism for implementation and analysis of sorting algorithms. The subsequent sections explore in detail the common sorting methods, their actual implementations, and performance analysis in terms of running time and memory space utilization. The unit also briefly reviews the techniques used for sorting the data stored on secondary storage devices. It concludes with an overview of searching methods applicable to arrays. The discussion is focused on the primary searching methods known as sequential searching and binary searching, and their comparative advantages and disadvantages. Objectives. After completing this unit, you should be able to understand the significance of sorting, distinguish between internal and external sorting, understand the logic behind the simple sorting methods of bubble sort, selection sort, and insertion sort. Comprehend the advanced sorting algorithms used in shell sort, quick sort, heap sort, merge sort, and radix sort. Distinguish between sequential and binary search methods. Compare the performance and relative advantages and disadvantages of fundamental search operations. Introduction to sorting. Sorting is a procedure for organizing a collection of data items in either ascending or descending order. The sequence of sorted data depends on the data type of element being sorted. The numeric data are always arranged according to their magnitude and sign. The character or string data are arranged according to the character set used on a particular computer. The collating sequence for characters can be ASCII, ABCDIC, or Unicode. ASCII is most commonly used. Unicode is useful for handling extended character sets in languages like Arabic, Urdu, and Chinese. Sorting is frequently applied to records in conventional files and databases. You would recall that in a database, each record consists of several data fields. Further, a record is uniquely identified by a key which may be composed of one or more fields. Records are normally sorted on a primary key. Sometimes we need to sort on a secondary key as well. For example, entries in a results sheet may be arranged by institutions and within institutions by grades. The associated data fields are referred to as sort keys. Benefits of sorting. Sorting is a fundamental and useful operation in several situations. First, sorting facilitates the task of searching a large data collection. It vastly improves the speed of searching. In time-critical applications, sorting precedes the searching operations. Sorting helps organize business information in a systematic and meaningful way. Invariably, a collection of business data is pre-sorted to generate reports, statements, and summaries. Sorting or indexing is a vital operation supported by Database Management System (DBMS). Much of the power of a database management system stems from the ability to provide rapid sorting on multiple data fields. Finally, sorting helps analyze large amounts of scientific and statistical data. Sorting is also useful in recognizing patterns or identifying trends in time series. While sorting is useful, it is potentially the most time-consuming operation. As such, sorting algorithms have been a subject of intensive research ever since the emergence of computers. Over the past, several sorting techniques have been devised which range from simple but less efficient to most sophisticated and highly efficient. In this unit, we shall study commonly used and popular sorting methods which are known as bubble sort, insertion sort, shelf sort, quick sort, heap sort, merge sort, and radix sort. Types of sorting. The sorting algorithms are classified into two categories: internal sorting and external sorting. When sorting is done on a data collection which is kept entirely in the main memory, it is referred to as internal sorting. In most real-life applications, however, all data to be sorted cannot be accommodated in random access memory and is instead stored in secondary devices such as disk, diskette, or magnetic tape. In this case, blocks of data residing on auxiliary storage is loaded into the main memory, processed, merged with data on the devices. This mode of sorting is referred to as external sorting. The external sorting is slow compared to internal sorting because data blocks to be sorted have to be retrieved in a sequential order from the secondary device. By contrast, in internal sorting, any record can be directly accessed from the main memory. Framework for implementation of sorting methods. Before considering some specific sorting algorithms, it will be useful to devise a general framework for the implementation of various sorting methods. As before, we shall use a C++ interface class to specify the operations for creating an array, performing sorting on the array, and listing the contents of the array. The structure of interface sort class is as shown. Briefly, it performs these steps. The class is designed to handle array X of fixed size determined by the constant array size. Constructor initializes the variable count, which keeps track of the number of elements added to the array. Add method is meant to add a number to the array X. Display prints the contents of array. Sort A is the main sorting routine. It implements a specific sort algorithm such as bubble sort, heap sort, etc. We shall consider the detailed coding of sort A method in the relevant section. The codes for add and display methods will be given in program demonstration. Once the sort class is developed, it can be used in the C++ function main to invoke the sort procedures as shown. Analysis of sorting algorithm. The techniques for the analysis of general algorithm were presented in an earlier unit. You would recall that the performance or running time of an algorithm is expressed using big O notation. For example, an algorithm has O (n) efficiency if the running time increases in direct proportion to the size n of input data. Here, we examine the specific operations that influence the running time of a sorting algorithm. In general, sorting involves the following operations: accessing, fetching a data item from memory, comparing, making comparisons between a pair of data items, swapping, interchanging pair of data items, assigning, storing data item in a variable. In some cases, assignment can be a part of the swapping operation. The comparing and swapping are the most time-consuming operations and normally considered in the analysis. Based on the complexity, the sorting algorithms are classified as elementary and advanced. The elementary methods use iterative procedures consisting of nested loops. Consequently, their efficiency is determined by the number of loops to be executed. In general, the elementary sort methods have O(n)² or quadratic runtime. They are not efficient because the running time increases quadratically with the increase in the number of items to be sorted. As we shall explore later, the bubble sort, insertion sort, and selection sort have time efficiency O(n)² and are characterized as elementary sort methods. The advanced sort methods are based on recursive procedures. In this case, the data to be sorted is partitioned into smaller blocks which are recursively sorted. This approach is often referred to as divide and conquer. The advanced sorting methods have O(n) log n runtime. Since n log n grows at much lower rate than n², the advanced algorithms are much faster compared to elementary methods. The quick sort, merge sort, and heap sort belong to the category of advanced sorting algorithms. In some cases, the efficiency of an algorithm also depends on the existing order of the data to be sorted. For example, in some situations, the data might appear in pre-sorted order, sorted in reverse order, partially sorted, or randomly arranged. Thus, analysis of algorithms must also consider the worst case, best case, and average case scenarios. In general, a set of n data items can be arranged in n factorial ways. The possible arrangements grow tremendously as the number of items in the collection increases. For example, a collection of 10 data elements can have over 3.6 million arrangements. An acceptable algorithm should cater for all possible appearances of data. In average case analysis, it is assumed that all of the n factorial arrangements are equally likely to appear. The analysis of a sorting algorithm boils down to counting all exchanges and comparisons during the execution of iterative or recursive procedure. At each stage, the array or subarray is scanned from one end to the other. The process of complete traversing the array is often referred to as pass in sorting terminology. Bubble sort. Bubble sort is the simplest of all popular sorting methods and easy to implement. It works by comparing two adjacent data items and swaps them, if necessary, to bring them in proper order. Usually, the array is scanned several times. During the first pass, the first and second elements are compared. If found to be out of order, they are exchanged. Next, the second and third elements are examined and swapped if necessary. This process is repeated until the end of array is reached. As a result of the first pass, the largest element bubbles up at the end of the array. In the second pass, the subarray, excluding the last element, is processed. The passes are performed until the subarray is reduced to a single element. An example of bubble sorting is shown. In first pass, first two elements, 56 and 89, are compared. Since these are in order, no exchange is required. Next, second and third element, 89 and 77, are considered. Being out of order, these are swapped. Then, element in third and fourth position, 89 and 10 are compared and swapped. Next element in 4th and 5th position, 89 and 84, are considered and exchanged. This brings the largest element to the last position. In second pass, elements in 1st and 4th position are processed. In the third pass, elements in 1st and 3rd position are considered. In the 4th pass, the array is sorted. Please click the button to watch bubble sort visualization. Implementation of bubble sort. Bubble sort is easy to implement. This figure lists the code for bubble sort method. Briefly, it performs these steps. We create two nested loops. Outer loop controls the passes. Inner loop iterates through the array to compare adjacent elements. Variable count is the total number of elements in the array X. This code fragment can be embedded into template class presented earlier to make a full-fledged program. Please click button to run interactive program for bubble sort. Analysis of bubble sort. We assume n is the size of array to be sorted. As discussed earlier, the bubble sort makes n-1 passes through the array in executing the outer loop. During pass 1, it makes at most n-1 comparisons. During pass 2, it makes at most n-2 comparisons, and so on. Thus, in the worst case, it will make a total of n-1 plus n-2 plus n-3 up to +1 comparisons. The above series adds up to n-1 by 2 is equal n square by 2 minus n by 2. Thus, running time of bubble sort in worst case is O(n square by 2 minus n by 2. Ignoring the lower term and constants of the efficiency is O(n square. Note that worst case occurs when the array is sorted in the reverse order. In the best case situation, the array is already sorted. In the improved version, bubble sort makes only one pass and makes n-1 comparison. Since no exchanges take place, the sort is terminated. Thus, in the best case, runtime is O(n-1 or O(n). Thus, although bubble sort is simple to implement, it is not efficient for use on a large data set. Selection sort. Selection sort is one of the simplest sorting methods. To sort the array in ascending order, the array is searched for the largest element, which is then exchanged with the element in the last position. Next, the subarray, which excludes the last element, is searched again for the largest element. When found, it is exchanged with the next to last element in the subarray. This process is repeated until the subarray reduces to a single element. At this stage, the array will be sorted in ascending order. The same procedure can be followed to sort the array in descending order. An example of selection sort is shown in figure. The sample array consists of 5 elements. In the first pass, the largest element is found to be 68. It is exchanged with the element 23 in the last position. In the second pass, the subarray comprising first 4 elements is searched for the largest element, which is 62. It is exchanged with the last element 23 in the subarray. In the third pass, Subarray consisting of first three elements is searched for the largest element. It is 23, which is exchanged with the last element 19. In fourth pass, the first two elements of the subarray are searched for the largest element. It is found to be 19, which is exchanged with the second element 10. The array is now sorted in ascending order. Please click the button to watch selection sort visualization. Implementation of selection sort. The selection sort method works in two phases. In the first phase, the array or subarray is searched for the largest element. To this end, a temporary variable is used which is initially set to the first element of the array. The array is then scanned by comparing each element with value held by the temporary variable. When a larger element is found, the temporary variable is reset to the largest element. At the end of the scan, the temporary element would hold the largest value in the array. In the second phase, the largest element is swapped with the last item. The process is repeated on the subarray. The code for selection sort is as shown. It uses variable xmax and imax to hold the largest value and index of the largest element. The variable count holds the number of elements in the array. It includes two nested loops. The outer loop performs passes over the array and subarrays. The inner loop iterates through the subarray to determine the largest value. Please click button to run interactive program for selection sort. Analysis of selection sort. As discussed earlier, the selection sort methods consist of two nested loops. If n is the size of input, the outer loop executes n-1 times. The inner loop executes n-1 times during the first pass, n-2 times during the second pass, and so on. Thus, the inner loop makes altogether n-1 plus n-2 plus n-3 plus up to 1 is equal to n-1 by 2 comparison over all the passes. At the end of each pass, the exchanges are made to find the largest value. Since the outer loop executes n-1 times, the total number of exchange will be. Thus, in the worst case, selection sort will perform comparison and exchanges. Thus, the total running time will be, or ignoring lower order terms and constant on square. Since running time increases quadratically, the selection sort is inefficient for sorting large data sets. Observe that compared to bubble sort, the selection sort makes fewer data moves. More specifically, it makes roughly n square by 2 comparison and n exchanges. Thus, selection sort is a better choice compared to other quadratic sort methods when data movement is time-consuming operation. For example, in sorting of files with records but small sort keys, selection sort is preferable. Insertion sort. Insertion sort is a simple and intuitive sort method. As the name implies, it systematically picks array elements and inserts them into proper positions. The array is proportionally divided into two regions, one with sorted items and other with unsorted items. In each pass, an element is picked from the beginning of the unsorted region and moved into the sorted part. In order to do so, all elements larger than the element being moved are shifted one position to the right to make room for the picked element. Figure illustrates the insertion sort procedure on an array consisting of 5 elements. To begin with, the first element 83 is considered as belonging to one element sorted region. The second element is then moved and placed before 83. This insertion requires 83 to shift to the right. In fact, 83 occupies the position vacated by 22. Next, element 29 is considered. It would need to be inserted between the elements 22, 83 in the sorted region. Thus, element 83 is moved one place to the right to make room for the element 29. In the next pass element, 77 is considered. It would need to be inserted between the elements 29, 83. To do so, the element 83 is shifted to the right. Finally, element 67 is processed. It is placed between the elements 67, 83. The array is now in the sorted order. Please click the button to watch insertion sort visualization. Implementation of insertion sort. Insertion sort can be implemented in different ways. A simple procedure uses two arrays, one to store the source data and other for insertion of sorted elements. To save storage space, it is usual to use in-place sort, which uses a single array for sorted and unsorted items. In fact, the approach was followed in the insertion sort examples discussed previously. The source code for insertion sort procedures for in-place sorting is given in figure. It sorts an array of floating point numbers stored in array X of size count. The procedure is based on two nested loops. The outer loop controls the passes over the array. The inner loop iterates to perform comparisons and does the shifting by moving an element to the right. The variable temp holds the elements to be inserted into the sorted sub-array. Please click button to run interactive program for insertion sort. Analysis of insertion sort. The preceding discussion shows that insertion sort method utilizes two loops. If n is the array size, its outer loop makes n-1 passes over the array. For each pass, the inner loop makes one or more iterations to make comparisons and shift the data. In the worst case, when the inner loop is fully executed, it makes 1 plus 2 plus up to n-1 is equal to n-1 by 2 comparisons and equal number of shifting in each pass. The outer loop assigns an element to a temporary variable and then assigns the temporary variable to an array element. Since outer loop execute n-1 times, it causes 2 n-1 data moves. Thus, altogether, the insertion sort performs n-1 plus 2 n-1 is equal to n square plus n-2 operations involving comparisons, shiftings, and assignings. Thus, running time of insertion sort is O(n) square plus n-2 or O(n) square. More precise analysis would show that on the average, insertion sort makes about n square by 4 comparisons and n square by 8 exchanges. Thus, even though insertion sort has quadratic runtime, it performs better than bubble sort and selection sort. It is, however, inefficient for large data sets comprising several thousand data items. Shell sort. Shell sort, named after its inventor Donald Shell, is designed to improve the performance of quadratic sort algorithm. It is an extension of the insertion sort. In shell sort, comparisons are made between elements that are distant apart. The displacement is called increment. In each pass, the size of increment is reduced, so that in the last process, comparison is made between the adjacent elements. For this reason, a shell sort is sometimes referred to as diminishing increment sort. Thus, if initially the increment is taken as 4, comparison will be between first and fifth element, then between second and sixth, and then between third and seventh element, and so forth. In the next phase, the increment may be set to 3 or 1, but in the last pass, the increment must be 1 so that adjacent elements are compared. It is usual to refer to each pass as 4 sort, 3 sort, 2 sort, and 1 sort. An example of shell sort is shown in figure. The sample array consists of 8 elements. In order to apply shell sort method, we choose a sequence 4, 2, and 1 for the increment. Accordingly, the sort phase are named as 4 sort, 2 sort, and 1 sort. In 4 sort phase, an element is compared with another element with relative displacement of 4. Thus, elements 11, 75 are compared and exchanged. Next elements 72, 58 are compared and exchanged. Then elements 83, 12 are compared and exchanged. Lastly, elements 64, 83 are compared. Since these are already in order, no swaps are done. In the 2 sort phase, element displayed by 2 are compared. Thus, element in the first position is compared with element in the third position. This procedure is applied till the last element in the array. In the last phase, 1 sort, the elements in the adjacent positions are processed. Thus, elements 11, 50 are compared. Since they are already in order, no action is taken. Then elements 50, 12 are compared and swapped to bring them in ascending order. This process is continued across the array. At the end, the array is in sorted order. Please click the button to watch shell sort visualization. Implementation of shell sort. The implementation of shell sort method is similar to that of insertion sort. However, 2 modifications are required. First, an appropriate sequence set would need to be specified. Second, the inner loop should be modified to compare and shift elements which are located apart according to the specified increment sequence. We assume the sequence 4, 2, 1 for the increments. Starting with initial value 4, the increment would be reduced by half after the first cycle and set to 1 in the last cycle. Please click button to run interactive program for shell sort. Analysis of shell sort. Analysis of shell sort is considered a major improvement on quadratic sort algorithm. Although it can easily be implemented, the analysis of its performance is difficult and quite involved. It has been a subject of several investigations since it was introduced. Various analytical and empirical studies show that the performance of shell sort is largely influenced by the choice of increment set. The inventor of shell sort has proposed the sequence 1, 2, 4 up to n by 2 for an array of size n. It has, however, discovered later that the choice does not produce the best results. An alternative set 1, 3, 7, 15 was proposed by Hibbard. With this choice, it is shown that in the worst case, shell sort has running time O n 3 by 2. Sedgwick has shown that with the increments 1, 4, 13, 40, 121, in the worst case situation, the shell sort has O n 3 by 2 running time. In the average case scenario, the running time is O n 3 by 2. Thus, in either case, shell has significant improvement over bubble sort, selection sort and insertion sort, which have running time O n square. As such, shell sort is a method of choice for sorting of moderately large data sets consisting of few thousand data items. Quick sort. Quick sort was proposed in 1960 by C.A.R. Hoare. Unlike the previously studied methods, which are based on iterative procedures, quick sort uses recursive algorithm. Broadly, a data set is partitioned into smaller subsets which are recursively processed. Thus, quick sort belongs to the category of divide and conquer procedures. Quick sort is among the fastest sorting methods and extensively used in a variety of situations. Because of its common use, several programming languages, notably C, C++, and Java, provide support for quick sort in standard libraries. The quick sort method works in two phases. First, the array is partitioned into two subarrays using one of the array elements as pivot, such that all elements to the left subarray are smaller than pivot and all elements in the right subarray are larger than the pivot. In the next step, the partitioning procedure is applied recursively to the left and right subarrays. In practice, several schemes exist to choose a pivot and partitioning of array into two subarrays. Later on, we shall see that the performance of quick sort is influenced to some degree by choice of pivot. Detail of procedure for performing this method is given in reference notes. Let us consider, for example, the array consisting of 10 elements. To apply quick sort, we follow the following steps. We select the leftmost element 60 as the pivot. The left and right pointers are set to point to the elements 60, 20, respectively. The array is scanned from right to left, beginning with element 20, skipping all elements that are greater than the pivot 60. Since 20 is smaller than pivot, we stop at the element 20. The element 20 is copied into the element pointed to by the left pointer, that is element 60. Next, the array is scanned from left to right, beginning with element 26, skipping all elements that are smaller than the pivot 60. The element 85 being larger than 60, we stop at element 85. The element 85 is copied to the element pointed to by the right pointer, that is element 20. The array is next scanned from right to left, beginning with element 85 and skipping all elements that are larger than pivot 60. Thus, we stop at the element 13. The element 13 is copied into the element pointed to by the left pointer. Next, the array is scanned beginning with element 31 and skipping elements that are smaller than the pivot, and stopping when left and right pointers cross over. Now, both the pointers point at element 13 between the element 4, 87 as shown. We now replace the element 13 with pivot 60 and obtain Observe that the element 20, 26, 13, 31 and the left of pivot 60 are smaller than the pivot, and the elements 87, 76, 73, 85 to the right of the pivot are larger than the pivot. We can apply the same procedure to the left and right partition until the array is sorted. Please click the button to watch Quick Sort visualization. Implementation of Quick Sort. The implementation of Quick Sort method consists of two parts: partitioning of array and recursive calls. For the partitioning, we shall follow the algorithm discussed previously. The implementation of recursive calls is simple and straightforward. Figure lists the complete code. It consists of two methods named QuickS and QSort. The function QuickS simply passes the upper and lower bounds of the array X to be sorted. The QSort is the main operative method for the quick sorting. It includes integer variables LB, RB and PA to hold the current values of lower and upper bounds and the index of the pivot. The variable pivot is assigned the leftmost element in the subarray. Code includes 3 while loops. The outermost loop tracks the left and right pointer and terminates when the pointer LL and RR cross over. The second inner loop scans the array from right to left. It decrements the pointer RR until an element lower than the pivot is encountered. The third while loop scans the array from left to right, incrementing the pointer LL until an element greater than the pivot is found. On termination of inner loops, the corresponding elements are swapped. When the outermost loop terminates, the value held by pivot is assigned to XLL. The last part of the code contains two recursive calls to process the left and right subarrays. Please click button to run interactive program for shell sort. Selection of quick sort pivot. Various studies show that choice of pivot has a significant impact on the performance of quick sort algorithm. As already discussed, the simplest choice can be either the first or the last element in the array. This is, however, not the best choice in all circumstances. For example, if the array is already sorted or partially sorted, the selection of the first element as pivot would greatly degrade the performance. To avoid such risks, several alternative methods have been proposed. Two common approaches are called random selection and median of 3 selection. In random select, an element of the array is randomly picked and assigned to the pivot. Experience shows that this is the safest choice. However, in actual implementation, we need a random number generator to produce numbers between the upper and lower bound of an array or subarray. This is an additional overhead and increases the running time. Another method, known as median of 3, selects the middle element as the pivot. For example, if LL and RR are lower and upper bounds of array X, the index of a middle element should be MM is equal to LL plus RR by 2. Thus, X of MM is chosen as the pivot. Most popular implementations of quicksort method follow this approach. Empirical studies show that the median of 3 choice not only avoids the risk of degradation, it actually increases the performance by 5 to 10%. Analysis of quicksort. As we have seen in the implementation of quicksort, the significant operations are partitioning of array into smaller arrays, comparisons of elements with pivot, and swapping of element during scanning of the array. In order to determine the running time, we investigate the total amount of these operations. Let us first consider the number of partitions. We have seen that at recursive call, the array is split into two sub-arrays of nearly equal size. Thus, if we have an array of 7 elements, it will be split into 3 sub-arrays of sizes 1, 2, 4, because 1 plus 2 plus 4 is equal to 7. Generally, thus, we can say that an array of size n can be split into at most log n plus 1 partitions. After partitioning of an array, we perform n comparisons and n exchanges in worst case. Thus, the total number of major operations involved in quicksort are 2n log n plus 1. We therefore conclude that the running time of quicksort is O2n log n plus 1, or ignoring constants, O n log n. The logarithmic function n log n grows much slower compared to the quadratic function n square. Thus, quicksort is far too efficient compared to the quadratic sort methods named bubble sort, selection sort, insertion sort, and shell sort. However, as noted before, the performance of quicksort is also influenced by the existing order of input data. The worst case occurs when the array is already sorted. In this case, if the leftmost element is selected as to pivot, the array will split into 2 arrays of sizes 1 and n-1. Thus, altogether, 1 plus 2 plus up to n-1 is equal to n into n-1 by 2 comparisons and exchanges would be performed. As a result, the running time would be O n into n-1 by 2, or O(n) square. Thus, the quicksort would perform as poorly as any quadratic sort algorithm. Another major drawback of quicksort is that it is massively recursive. Recursion is generally performed by using computer's special memory known as heap. For problems involving a large number of recursions, enough memory may not be available on a particular machine. Further, some of the programming languages do not support recursion. Despite these drawbacks, quicksort is by far the fastest general-purpose algorithm. Heap sort. As the name implies, heap sort method uses a special data structure called heap to perform sorting. Heap is, in fact, a special kind of binary tree with 2 distinguishing features referred to as order property and completeness property. The order property implies that each node of a heap contains an element that is larger than both left and right children. It follows that in a heap, the largest element will always be located at the root. The completeness property means that all nodes of the tree up to the bottom level are filled. The bottom level is filled from left to right. An example of heap is shown in figure. Observe that each node contains an integer value which is larger than the values located in the child nodes. Further, the largest number 86 is located at the root of heap. The tree nodes are filled up to the 3rd level. The bottom level has only 2 nodes with values 31 and 64, which are located in the leftmost positions. The heap sort method is based on the observation that in a heap the largest element always appear at the root level. Thus, heap sort algorithm consists of following steps. Map the array into a binary tree. Convert the binary tree into heap. Remove the topmost item at root level and place it at the end of the array. Move the element in rightmost bottom nodes to the root of tree. Repeat step 2 through 4 until the tree is empty. Quite obviously, the two main steps are mapping the array into a binary tree structure and converting the binary tree into heap. We first examine these steps in some detail. Mapping array to binary tree. Transforming an array into a tree structure is relatively simple matter. Using array elements, the binary tree is constructed in top to bottom and left to right order. Thus, the first element is placed at the root. The next two elements are placed as the left and right child nodes, and so on. Figure shows an example of an array and its corresponding binary tree. The number next to nodes indicate the tree order and corresponding indexes in the array. Converting tree into heap. In heap sorting, conversion of tree into a heap, commonly referred to as heaping, is a major task. Two common algorithms follow either top-down or bottom-up approach. In top-down procedure, the heaping process is started at the root level and proceeds down to the bottom level. In the bottom-up method, the reverse order is followed. We shall follow the top-down procedure in the subsequent discussion of heap sort. The heaping procedure will be as follows. Starting with first child of the root node, systematically consider all its elements up to the last leaf node. If an element is smaller than its parent, then swap the contents of pivot and child. If no exchange is required, move to the next node. Otherwise, continue repeating step 2 until the root is reached. Figure illustrates the heaping process. In the diagram, arrows show the movement of elements. Heaping process proceeds as follows. 31 and 58 are exchanged. Next, node 3 is examined. It contains element 60, which is larger than the element 58 at root node. So, 58 and 60 are exchanged. Then, node 4 is considered. It contains element 38, which is larger than the element 31 in the parent node. Thus, 31 and 38 are swapped. Next, node 5 is processed. It contains element 67. 38 and 67 are swapped. Node 2 now contains 67, which is larger than 60 in the parent root node. Thus, 67 and 60 are exchanged so that element 67 moves to the top. Then, node 6 is processed. It contains element 70, which is larger than the element 58 in the parent node. So, element 58 and 70 are exchanged. Next, node 7 is processed. It contains element 69, which is larger than the element 67 in the parent node. Therefore, the elements 69 and 67 are exchanged. Finally, node 8 is processed. It contains element 86, which is larger than the element 31 in the parent node. Therefore, 86 and 31 are swapped. Node 4 now contains 86, which is larger than 60 in the parent node. Therefore, 60 and 86 are swapped. The node 2 now contains 86, which is larger than 70 in the parent root node. Therefore, 86 and 70 are exchanged. Thus, element 86 moves to the root. The tree is now fully heaped. Please click the button to watch visualization of heap sort procedure. Implementation of heap sort. The code for implementation of heap sort procedure is shown in figure. It contains two methods named hsort and crheap. The function hsort is called by the user program. It sets the size of array, then invokes the crheap heap creation method. The crheap converts the binary tree into a heap. The size of tree is passed as an argument to crheap. Click the button to run interactive program for heap sort. Analysis of heap sort. In heaping, an element is compared with its left child and swapped if child holds a larger element. It is then compared with the right child and swapped again if the right child holds a large element. In moving down an element, two comparisons and at most two exchanges are performed. We conclude that during reheaping, four major operations are performed at each level of the binary tree. In a preceding unit, we have seen that a binary tree of size n has at most log n levels. As such, the total number of comparisons and swap would be 4 log n. In general, the largest and smallest elements are swapped n times. This means that the total number of major operations involved in the reheaping is at most 4n log n. Therefore, the running time of the heap sort is O 4n log n or O n log n. Thus, heap sort has the same asymptotic behavior as the quick sort. Further analysis shows that heap sort is somewhat slower than quick sort. It is definitely faster than the quadratic sort algorithm. Heap sort has some advantages over the quick sort. First, unlike the quick sort, it is not recursive. Second, compared to quick sort, it is more robust. This means that the performance of heap sort does not depend on the state of input data. It is always guaranteed to be proportional to n log n, irrespective of the fact whether the input data is partially sorted or random. For such reasons, heap sort provides an ideal solution for sorting of data in real-time applications, because order of input data cannot be predicted in such situations. Merge sort. Merge sort is among the earliest of sorting techniques. It was used in electronic data processing applications for processing of data stored on magnetic tape files. In this method, we take two sorted subarrays and merge them to create a new array. To this end, the elements in the two subarrays are progressively compared. The smaller of the two is copied to the new array. This procedure is repeated until one of the subarrays is finished. The remaining elements of the other subarray are then copied to the new array. The merge sort procedure can be recursive or iterative. In recursive method, the array is partitioned into two nearly equal subarrays which are recursively sorted. In the non-recursive procedures, the array is partitioned into a number of subarrays, each consisting of just one element. Each pair of one element array is merged with the adjoint pair. Next, the merged array is partitioned to subarrays, each consisting of two elements. Then, two-element array is merged with the adjacent two-element array. Thereafter, array is partitioned into four-element subarray which are merged. This process is continued until no further partitioning is permissible. Figure illustrates the merge-sort procedure. The array consists of 10 unsorted elements. First, the array is split into one-element array, each containing the elements 90, 64, 10, 87, 46, 42, 37, 73, 8, and 71. Then, elements in the adjacent subarrays are compared. The first subarray contains 90, which is compared to 64 in the adjacent subarray. Since 64 is smaller, it is first copied to the auxiliary array and then element 90 is copied. Next, the pair of arrays containing 10 and 87 is considered. First, 10 is copied, which is followed by 87. This process is continued to the end. In the second phase, the auxiliary array is split into subarrays, each containing of two elements. Thus, the first array contains 64 and 90, and second contains 10 and 87, and so forth. The two elements array are then merged. In the third pass, the auxiliary array is again partitioned into subarrays, each contains four elements. The four-element arrays are merged into an auxiliary array. Finally, an 8-element subarray is compared with remaining two elements, 8 and 71. The two subarrays are appropriately merged to produce an auxiliary sorted array. Click the button to watch visualization of merge-sort procedure. Implementation of merge-sort. The code for implementation of merge-sort method msort is listed in figure. It uses a variable ps which holds the partition size. It is initially set to 1 to partition the array into subarrays of one element each. At the end of a pass, the partition size is doubled. A while loop controls the partitioning process. It terminates the procedure when the partition size exceeds or equals array size. An auxiliary array, AX, is used to hold the merged subarrays. Variables J1, K1, J2, K2 are used to define the boundaries of the subarrays being merged. Variables J and K points to the elements of subarrays. A while loop checks that J remains less than or equal to J1 and K remains less than or equal to J2. A smaller of the elements in the subarray is picked and copied to the auxiliary array. The variable m determines the number of elements copied into the auxiliary array. After either of the subarray is exhausted, then remaining elements of this other subarray are copied to AX. After all the subarrays have been merged, the auxiliary array AX is copied back into the original array X. The process is repeated with a new pair of larger subarrays. Click the button to run interactive program for merge sort. Analysis of merge sort. In merge sort, at each pass the size of partition is doubled until it equals the size of array being sorted. Thus, the number of passes is equal to the number of partitions. While discussing quicksort, we saw that an array of size n can be split into log n partitions of sizes 1, 2, 4. Thus, the merge sort procedure of n data elements involves log n passes. During each pass, at most n comparisons are made. This means that altogether n log n operations are performed. In other words, the running time of merge sort is O n log n. Thus, merge sort has the same running time as quicksort and heap sort. Empirical studies show that merge sort is marginally faster than heap sort, but slower than quicksort. A major drawback of merge sort is that it requires extra storage space to hold the auxiliary array. Thus, space efficiency of merge sort is On. For very large data sets, the requisite space may not be available on a particular computer. Further, the process of data movement between the main and auxiliary array considerably slows down the sorting. Radix sort. Radix sort is an adaptation of an old procedure which was used to sort punch cards on a mechanical sorter. It was invented by H. Seward in 1954. Radix sort method can be used on a data collection when all data items lie in a small fixed range, such as decimal digits, characters, or binary digits. For each data item, we need a method to identify the bin to be allocated in each pass. The range R is often called radix. Thus, we have R is equal to 10 for decimals, R is equal to 26 for alphabets, and R is equal to 2 for bits. Click the button to watch visualization of radix sort procedure. Implementation of radix sort. The code fragment for implementation of radix sort is listed in this figure. It contains two classes, Q and radix. The constant iSize defines the maximum number. It also defines the total number of passes. The class Q includes three methods named insert, remove, and isEmpty. The class radix implements the sort method. It uses an array of queues named QUE to serve as bins for the sort method. In a sense, P determines the integer value in x of j for the ith pass. Accordingly, x of j is moved to the QUE of P. Please click the button to run interactive program for radix sort. Analysis of radix sort. The major operation involved in the radix sort are extracting the digit or character positions, computing bin number, and merging data with the array. Suppose S is the maximum size of a data item and R the possible range or radix. R would equal 26, 10, or 2 for alphabets, integers, and bits respectively. The radix sort will make S passes. In each pass, it would make at most R comparisons to allocate a bin. It would, for instance, check if a particular queue is empty. If n is the size of data input, altogether total number of S into R into n major operations would be performed. Thus, running time of radix sort is O S into R into n. S and R have fixed values. Thus, if the input data consists of short unsigned integer, the radix sort can have O(n) running time much faster than other sorting algorithms. In the worst case, when keys are very large, S may be the same order as N. Thus, radix sort will have O(n)² performance. A major drawback of radix sort is that it is space-wise not efficient. It requires large memory spaces to serve as bins. The performance of common sorting methods in terms of running time utilization is summarized in figure. As shown, the sorting algorithm fall into two major categories designated as quadratic and logarithmic. Obviously, logarithmic algorithms have much better efficiency. Bubble sort is simple and may be used for very small data sets. Selection sort can be used for small data sets with small keys and large record sizes. Insertion and shell sort give best performance among the quadratic algorithms. They can be used for moderately sized data sets. Among the logarithmic sort methods, quick sort gives best performance if the input data is randomly distributed. The heap sort is the best choice when distribution or order of input data is not predictable. It is a robust method with guaranteed logarithmic performance in all situations. Merge sort has somewhat better performance than heap sort. However, it requires memory space as large as the array to be sorted. For a very large dataset, it may not be a good choice. The radix sort shows good performance if the dataset has short integer keys. We conclude that choice of sorting method is dictated by the size of keys, size of dataset, and pre-existing order of the input data. Another consideration is the amount of available storage space for auxiliary arrays or queues. Sorting. As mentioned earlier, external sorting refers to sorting of data residing on secondary storage devices such as tapes, disks, and diskettes. In this case, the major time-consuming operations include reading from and writing to the external storage. To sort a large data file, records are read in blocks and loaded into the main memory. Each block is sorted internally using a suitable method and is written back to the secondary device as a sub-file. The smaller sets of files are then merged into a single sorted file. The merging of sub-files is essentially based on the same technique as used in internal merge procedures. Since movement of large records is a time-consuming and costly operation, in practice, relevant sort keys are stored in a separate file with pointers to record in the main file. This file is referred to as index file. The index file is sorted by the relevant key. The sort file together with the record pointer can be used to list records in the main file. In general, it is possible to create indexes on several fields. Figure shows an example of index file used with the personal file. File 1 is the main file. File 2 is index file for ID. It is sorted by ID number and contains pointers to the record in file 1. File 3, sorted on name, is the second index file. It also holds pointers to the personal file. Suppose we want to access the main file via index file, file 2. Using pointer, we can list the records in the main file in order of ID. Again, using pointer in file 3, we can access the main file and list records sorted by names. The indexing has following advantages. The size of the file used in external sorting is tremendously reduced. Arrangements of records in the main file is not disturbed. Thus, not only the time in data movement is saved, the chances of corrupting the files are eliminated. If the records in the file are added, deleted, or updated, the index file is updated more efficiently compared to sorting of whole file. Searching. Searching is the process of locating an item in a data collection. It is an important activity in several computer applications. In fact, a large amount of time of millions of computers in Internet is spent in searching a large variety of databases. The searching techniques differ with size and complexity of data structure. We have already studied the method for searching binary trees. Two advanced search methods known as breadth first search and depth first search are used for locating a specific item in a complex data structure. It is commonly used on trees and graphs. We shall explain these techniques later. For now, we explore two simple methods normally used to search arrays. These are categorized as linear search and binary search. Binary search. A binary search can be performed if the array is in sorted order. In this method, an element to be searched is compared with the middle element of the array. If the middle element is greater, the search is continued to the first half of the array. On the other hand, if the middle element is smaller, the first half of the left is ignored and search is performed on the second half. This process is continued until either a match is found or the search area shrinks to zero size. Note that at each step, the array to be searched is reduced by half. Figure illustrates the binary search method. The element 28 to be searched is first compared with the middle element. The index of middle element is 0 plus 12 by 2 is equal to 6. Thus, 28 is compared with 45. Since 45 is larger than 28, the search is now restricted to element 0 through 5. The index of the middle element in the subarray is 0 plus 5 by 2 is equal to 2. The new middle element is 12. Since 12 is smaller than 28, it is next confined to element 3 through 5. The middle element of this subarray is 28, which matches with the element being searched for. Linear search. Linear search or sequential search is used for searching arrays in which data items are not in a specific order. In this method, beginning with first item, each item is successively compared with the item to be searched for. This process is continued until either a match occurs or the array is exhausted. The process of searching of an array is illustrated in figure. Click the button to watch visualization of linear search procedure. Implementation of linear search method. The implementation of a linear search method is quite simple. Figure shows a listing of code fragment. It is designed to search an array X of integer for a value held by the variable key. The array is scanned in a loop. If a match occurs, the index of the matching element is returned. If the loop terminates without a success, -1 is returned. Please click the button to run interactive program for linear search. Analysis of linear search. To search an array of size n, almost n comparisons are made between array elements and items to be searched if the element happens to be non-existent or if it is the last element. Thus, in a worst case, the running time of linear search is O(n). the average number of comparisons would be n by 2. In the best case scenario, the elements being searched for is the very first item. Thus, in the best case, the efficiency of linear search is O1. Linear search is not an efficient search method, but if the array consists of randomly distributed elements, choice is restricted to linear search. Implementation of binary search method. An implementation of binary search method is shown in figure. Code includes a search method named bsearch. It is meant to search an array X of size count. It received an argument key of type integer to be searched for in the array. A loop is set up to scan the array. At each iteration, it computes the index of the middle element using variable left and right, which identify the left and right boundaries of the sub-array. The key is compared with the middle element. If middle element is larger than key, variable right is set to middle, where middle is the current index of the sub-array being scanned. If middle element is smaller, left is set to middle plus 1. This process is continued until key matches with the middle element and value held by middle is returned. Otherwise, -1 is returned, which signals that search has failed. Please click the button to run interactive program for binary search. Analysis of binary search method. We have seen that in the binary search method, at each step, the size of array to be searched is reduced by half, and a comparison is then made with the middle element. Thus, the number of comparisons is equal to the total number of partitions of sizes 1, 2, 4, and so on. If n is the total number of elements in the array, then, as discussed earlier, the total number of comparisons would be log n. Thus, binary search method has running time O log n. The logarithmic function grows much slower as compared to a linear function. A comparison of the two functions is shown in figure. The binary search method is more efficient as compared to the linear search method. For example, in order to search an array consisting of 1 million items, we would need to make around 20 comparisons. A linear search of the array of the same size would involve about 50,000 comparisons on the average. A major limitation of the binary search method is that the array should be pre-sorted. This step itself would be time-consuming for a large array. For very small data set, however, there will not be much difference in the linear and binary search methods. Further, the binary search method is not applicable to other data structures in which the middle element cannot be directly accessed. For example, it cannot be used on a linked list because there is no simple way to identify and access a middle element.